Okay, welcome. My name is Ken Peters, and today I'm going to talk about deconvoluting mixed petroleum and the effect of oil and gas condensate mixtures on identifying petroleum systems. My co-author in this work is Andrew Murray, and we want to thank GeoMark Research for access to their geochemical database for much of the data we used in this work. Despite documented pitfalls, many geoscientists today are continuing to publish problematic oil-to-oil correlations based on compound ratios for dead oil that lacks volatiles. This issue is something that got Andrew and I interested in doing this research. So we're going to talk about this in this presentation. And what we want to do is first start with a description of the purpose. What is the impact of mixed light and heavy petroleum on fluid source assignment? That's correlation. We also want to talk about the impact of these mixtures on physical properties. The example we're going to use here is the gas-liquid ratio. We will use GLR, gas-liquid ratio, because unlike GOR, we want to also include oil as well as gas condensate. Biomarker concentrations for 4 pairs of petroleum fluids having very different GLRs from 100 to 50,000 standard cubic feet per barrel were mathematically mixed. This is a little bit of a unique, novel way of approaching this. We mathematically mixed these in 5% increments. So we've got 4 pairs of mixtures, each a binary mixture in 5% increments. Each series of mixtures was evaluated for genetic affinity by chemometrics, hierarchical cluster analysis, or HCA, and for source allocation by alternating least squares regression. We did this a couple of ways. We used alternating least squares regression of ratios, and we also did it using concentrations. I will open by saying that we know that ratios, where the denominator is different between the two end members, ratios mix as curves, whereas concentrations mix linearly. They are linear. Sure, concentrations are also ratios, but for example, ppm, we've got a 1 million in the denominator for both end members, so they mix in a linear fashion. The ratios we're going to use are some common biomarker ratios. Most of these are homolog ratios that are useful for establishing genetic relationships among samples. Okay, so I'm going to show you now the 4 pairs of mixtures. We have a pair from Taranaki. This is a Taranaki Koli source. It's an oil. It has a GLR of 1,000. We're going to mix it with Central Sumatra. The Kustran oil has a low GLR, again, an oil of 100. Okay. We're going to focus more on this one right here. These are mixed 2 oils. Now we're going to mix an oil with a gas condensate in the Selfviking graben. You wouldn't expect to see this in nature because these are 2 different basins, but here we wanted to mix 2 oils together here. But here we want to mix an oil with a gas condensate to see the effect. And you can see here the difference here is a GLR of 12,600 for the high GLR end member, which is the Schleipner-Huygens sourced gas condensate. And the oil has a GLR of 1,000, and it's from the Upper Jurassic drop deformation source rock. Notice the ratio of the 2 GLRs is increased here. And then we have 2 more examples down here where we mixed mathematically these end members. In the North Sea, we mixed a Kimmeridge oil with a Pentland, Middle Jurassic Pentland gas condensate. And here in the Perth Basin, you see you have an extreme case where we're mixing Triassic oil with a low GLR with an extremely high GLR and a gas condensate from the Permian source rock there. I'll focus on this one today. We just don't have time to talk about the others, but I will include the data and the figures for all of these so you can go back at your convenience and have a look at these in more detail after the talk is over. So here is the hierarchical cluster analysis for all of those 5% incremental mixtures, these binary mixtures. Here are the 2 oils that we mixed from Sumatra and Taranaki. Here's the Selfviking graben. Here are the samples from the North Sea, Norway, and UK. And here's the Perth Basin. You notice they form nice little superfamilies here. However, we have some outliers. And the outliers are, it turns out, the Coley end members for these three mixtures. And the Coley end member is always in red here, whereas the oil is in green. So you can see we have something that's very misleading. Hierarchical cluster analysis works best when you're dealing with oils from single sources. Right? Here we have mixtures. We know we have mixtures. We've made the mixtures mathematically, and we're getting pretty tight clusters here. For example, in the Selfviking Graben, nearly all of the mixtures plot with a tight cluster here, very similar to the composition of the Dropney oil. But some of these contain up to 95% Sleipner-Eugen gas condensate. So there's an issue here related to geochemical correlation or genetic assignment using hierarchical cluster analysis when you're mixing end members that differ dramatically in GLR, right? You remember this cluster analysis was based on C15 plus biomarker ratios that I just showed you. Well, a gas condensate, most of the mass there is in the range of C1 to C15. If you want to use linear regression, you need to include the entire range of molecular weight in the compounds that you analyze. You're not analyzing those in your metric analysis, so they're ignored, and you pay the price here. They're looking all like Dropney oil, except for the end member, which is down here. Okay, let's take a look now. I'm going to show you a table for the mix of the Sumatra and the Taranaki, and we're not going to go into detail here. I'm just going to go on to the Selfviking Graben. The table I'll explain it for the Selfviking Graben, and also the figure that follows is always explanatory in terms of what was in the table. So let's look at the Selfviking Graben. It's a nice illustration of the issues we're talking about here because we're mixing oil with gas condensate, whereas here for Taranaki Sumatra, the issues are not as severe, although they still are severe because we're mixing oils that have similar GLRs. Okay, so here is the Selfviking Graben. This is from a paper by Chris Cornford, and you can see part of the issue here. We have a well-established source rock here, the Upper Jurassic Dropney, which is the equivalent, basically, of the Kimmeridge Clay Formation. Very high hydrogen index, makes lots of oil. However, if you look at geochemical logs in this basin, there's also some pretty good source rock down here in the Huygen and the Sleipner. These generate gas and gas condensate. They're mostly terrigenous organic material, and so they're generating a gassy an end member that mixes with this oil. We're going to call that SVG gas. There was a paper published in 2003 by Richard Patchins, and he asks, where did all the coal gas go? And I think I'll show in the next few slides, it's there, but we don't see it. You don't see it if you use the standard geochemical approach or use the standard chemometric approach to identify that high GLR end member, that gassy end member. Okay, so here's our cluster diagram again. You can see all the samples are plotting very close together. Even samples that contain 95% of the Coley end member. 100% of the Coley end member is very different, of course. So we'll call this the Dropney subfamily. And if you did this analysis and didn't know these were mixtures, you might just say, well, geoscientists might just say, well, this is a organofacies variations within the Dropney formation. Not so. We know the truth here is that we mixed these two end members, and we're looking at the chemometric results based on looking at those ratios in hierarchical cluster analysis. Okay, so here's a table, and this should serve to help you interpret all the other tables that I'm going to include in this presentation. You can see here a blow-up of the hierarchical cluster analysis dendrogram. This sample GIT is, again, the end member. It's the gassy end member, 100% of the SVG gas in the mix. But the other samples all sort of plot together, very similar to each other, some sort of subfamilies here. Look at the green subfamily, exemplified by GQB. Sample GQB, a mathematical mix. It's 100% Dropney oil. All these other green samples down to 65% Dropney oil plot in this group. So 65 to 100%, they're plotting in this group. Then we have these white samples right here, and you can see exemplified by GZI. These guys range from 40 to 75% of the Sleipner-Huygens gas condensate in the mixture. But they're still looking very similar. There's not much cluster distance there. They're looking very similar to the drop me oil. And again, you see this group, the pink group down here, is beginning to pull away, but it's still at the scale of the previous cluster diagram, the dendrogram. They're basically the same or very similar to the drop me oil. Let's look at one sample in particular, PXM. PXM is right here, and you can see the mix. The truth here, the mix is 90% gas condensate from the Sleipner-Huygens, 10% drop me oil. Now, let's use alternating least squares regression of the ratios that I showed you earlier, those 17 ratios. A standard approach. A lot of people are doing this approach right now. There are papers being published on this right now. Let's calculate then and deconvolute that mix. What happened? This says 8% SVG gas, when in fact the mathematical mix is 90%. So we're seriously underestimating the Coley input to this mixture. Why? Because we're analyzing dead oil, C15 plus, and the ratios don't mix in a linear fashion as well. So the predicted GLR, if we knew it was 90% of the high GLRN number, the predicted GLR would be 11,500. But if you relied on this analysis, alternating least squares of ratios, you would predict a GLR of 8 is about in here, that you predict a GLR of about 2,000. So you would seriously underestimate the gas-liquid ratio. Why is that important? Well, in exploration, it's nice to know, and when you're drilling wells, it's nice to know what kind of gas content, what kind of volatile content, what kind of GLR you will have in your discovery. And this is a serious issue right here that I think a lot of people don't recognize. All right, so I said we would look at alternating least squares of concentrations, and we did it two ways. First of all, we just took the concentration data directly from the database. This is whole liquid concentration data, so it's based on C15 plus ppms, right? And so the concentrations here, if we use ALS of concentrations on a whole liquid basis, C15 plus, we still don't get the right answer. You can see we're still quite a ways off from the actual mix, and 75% as opposed to 90%. However, if we go back to the PVT reports and also the geochemistry, we can do mass balance, and we can use the power of linear regression by accounting for the missing mass that's missing in a dead oil. So we can calculate the amount of C1 to C5. We can calculate the amount of C6 to C15. We can add those into the mass and recalculate our parts per million. It's not a major effort. And then if we run alternating least squares, then we get a result that is exactly the same as the mix. Okay, so we're going to predict 11,500 for the GLR, and we're going to know that this is 90% SVG gas, Sleipner-Huygens gas, not 8%. That's a very important thing for people to take note of. As I said, there are a lot of publications right now that ignore that issue. So here's a figure then that follows each of the examples, tables that I show. This figure explains in a simpler way what I just showed you in the table. This straight line shows the mass in the mathematical mix of the gas source, the Sleipner-Huygens gas source. And if you calculate that using ALS, you should get the same result, right? So this is what you want to get right here. Okay? So what's happening? The ratios are mixing in a nonlinear fashion. And furthermore, you're not going to even see that gas condensate input, the Sleipner-Huygens input, until you get over 90% of SVG gas input, right? This is severely underestimating the Coley Sleipner-Huygens input, and the gas-liquid ratio is going to be severely underestimated as well. Then if you use whole liquid concentrations, just use the ppm data based on C15 plus, you're still not getting the right answer. If you normalize and do a mass balance, so you're looking at C1 plus whole fluid alternating least squares, you get spot on. You're able to predict exactly what the deconvoluted composition is of that binary mixture. Well, turns out isotope ratios have the same issue. you'll recall we have our oily end member, the drop me end member there, has an isotope composition of the saturates about -30. And we can do a calculation here because we know what the other end member is. This is the gassy end member. And so we have a curve here that represents the isotope composition of these 5% mixtures, right? So you notice here, up to about 80% of the gassy end member, the Sleipner-Huygens end member, you really don't see much of an isotope change at all. 1 per mil, you might ascribe that to organophase variations. Only after 80% do you start to see the isotope value approach that of the gassy end member. So where did all the coal gas go? It's there, but your analytical techniques and your chemometrics are being applied improperly. You're not going to see that end member, that gassy end member. And that also applies to your prediction of gas-liquid ratio. You will be off on your prediction of gas-liquid ratio. It will be much higher than you would predict based on just looking at the isotope value itself. Okay, so I'm not going to discuss 3 or 4. We're just going to fly through those. You can see I have a table and a figure for each. And again, you see this extreme underestimate of the Coley input. This is Pentland input here, very underestimated using ratios. Here is the extreme example from the Perth Basin. And you can see it's even more pronounced here. We see, again, that the Permian input and the GLR will be severely underestimated by the standard geochemical approach. The isotope problem is even worse in the Perth Basin because the isotopes really are not going to show much change at all until you have more than 80% Permian gas in your mixture. Okay, so here are my conclusions. HCAF compound ratios identifies genetic fluid families. It does. Through a range of molecular weight, you have to specify that molecular weight range. If you're dealing with dead oil and you're dealing with biomarker ratios that are C15 plus, that's the only range you can say anything about. It can be misleading for mixtures of end members with distinct compound concentrations and gas-liquid ratios. Alternating least squares of ratios can deconvolute oil-oil mixtures having similar GLRs. For example, 2 oils from the same source rock separated by a sealing fault. The oils on one side might have had a little bit different filling history. Maybe this is a little more biodegraded. This is maybe a little more water washed. So some very slight differences. So the denominator in the ratios is going to be similar between these two. So superficially, you're going to have a linear relationship with the mix and the GLR, but the mixtures are going to, it's going to be linear and it's going to work for oil-oil mixtures fairly well. But as soon as you have mixtures having very different GLRs or compound ratios or concentrations, they're going to mix in nonlinear fashion. Alternating least squares of ratios fails to deconvolute mixtures of oil and gas condensate. It underestimates the GLR and the contribution of that gas condensate. Alternating least squares of concentrations, you can use it to deconvolute binary mixtures. It also works for 3 and even 4 end members. But the quantification requires internal standards. So many labs, especially archive data, many labs, both industry and service company labs, have stored data that they did not use internal standards, so they can't give you ppm concentrations. All they can do is give you ratios, so you're in a difficult position there in terms of interpretation. ALSC of whole fluid, that's the way to go. You need to do a mass balance and account for the C1 to C15, as well as the C15 plus. That's a full mass balance. Those ppms will give you a good deconvolution of the oil. Many interpreters use ALSR of ratios to deconvolute mixtures, and there's still papers coming out on this, thus yielding inaccurate results. I've spoken with some of these people, and many of those will say, well, we trust the results. We're confident because we're very reproducible. This can be reproduced several different ways. We always get the same answer. I would suggest they look at this figure up here. This is very reproducible, very precise, but is it accurate? So you need to evaluate the mixing and the relative concentrations of compounds before you try to do deconvolution or even correlation.